Hello everyone. So last segment we talked about how we can analyze an algorithm, how we can calculate the order of an algorithm using big O notation. Now we can also represent an algorithm using two other way known as omega or theta. So let's first see the omega of function of n. So an algorithm A is omega of Fn. We can represent an algorithm as an omega of Fn if it consists C and N naught, okay, for which we can find that A requires more than C of Fn time units to solve the problem. All right. So here what it is saying that if we have a runtime function Tn, all right, and if we have a f of n for which we can find a value of c, okay, and if we can say that like t of n is always going to be greater than or equal to c of function of n, we can say that the algorithm A we can represent as a omega of function of n. All right, so here in this graph, you can see that this is our runtime function. All right. So this is our runtime function. And here, this is our runtime function. Now, this is our runtime function Tn, and here we have our Tn. So in big O notation or in using the to represent the upper bound runtime of algorithm, we are going to find a function of n, okay, for which we can say that c of f of n is always going to greater than the value of tn, okay. Then we can represent that using big O of f of n. But if we can find that like c of fn is always less than t of n for a value of n, all right, then we can represent this algorithm as a using omega notation, omega of fn. All right, so omega of fn actually gives us the idea of best case scenario, okay. So for the best case scenario means for the best case scenario, what can be the runtime of the algorithm, okay. Now there is another notation we can use, theta of fn. So algorithm A is theta of fn, denoted as theta of fn, if there consist two constants c1, c2, all right, and there exists a value of n naught such that c of fn is less than or equal to t of n less than or equal to c2 f of n. So if we look at the theta n, the idea is that this is our tn, all right, and we can see that we can find the value of c1 and c2 like that, all right, for which the value of c1 fn is going to be less than tn, and the value of c2 fn is going to be greater than tn, means tn is going to be in between of these two values, okay. So the theta of n is going to give us the idea of exact runtime of the algorithm, all right. So let's see the comparison of growth rate function, okay. So growth rate function gives us the idea that how our algorithm works when the input size is growing, okay. If we have only a small amount of input, in that case actually any algorithm may work with a small amount of input. But why do we have to be too much concerned about the efficiency of the algorithm, okay. So when our input size is growing, in that case we have to measure whether our algorithm is working perfectly fine or not. Okay. All right. So let's compare with growth rate function, and we can actually see how significantly our algorithm may differ in terms of growth rate function, okay, when our input size is growing. So let's see these are the growth rate function. Okay, so one means actually constant. Okay, so these are the growth rate function: constant, log n log n square, n cube, and 2 to the power n. So if the input size is 10, so 10, you can see that it's always fixed. We are just telling that here we are representing the constant amount, let's say just with 1. Okay. And using big O notation, if the runtime is constant, we also represent that as order of 1. Okay. So as this is a constant function, means whatever the runtime, whatever the input size is, runtime doesn't depend on the input size. This is always same. So with log n, you can see that with 10 input, the runtime is 3. And here we have 1 million of input. Okay, with 1 million of input, the runtime is 19. All right. Now with n, so if the growth rate function is n, with 10 input it's 10. Okay, but with millions of input, this is 10 to the power 6. Now let's see you have an algorithm A that has order of log n. Okay, and you have an algorithm B that has order of n. Now if the input size is 10, or let's say even 100, okay, so the time difference is say 6 versus 100. I mean, with a nice configuration of computer, with a nice processor, this may not actually, this difference is not significant. But now look at this difference. Okay, when our input size is really large, the difference, you can look at that, 19 versus 10 to the power 6. It's a huge difference. It is going to make a huge difference. All right. Now think about any other growth function which is worse than that. Just think about this 10 square. So 10 square, let's say you have another algorithm, order of n square. Okay, now think about that. Compare this one, 19 versus 10 to the power 12. Okay, so this is a huge difference, and obviously we are not going to pick this algorithm. Okay, obviously if we have an algorithm which has a growth function log n, obviously this is the better one. This is the one we are going to pick. Okay, so we may not have luck to find a solution log of n for all kind of problem. Okay, but obviously if we have to choose between n versus of n square, n versus n square, still actually this makes a huge difference, 10 to the power 6 versus 10 to the power 12. All right, so here by looking at this value, you can see that how our algorithm is going to working when our input size is growing. Okay, now for 2 to the power n, so this is the actually worst type of algorithm, and we're never going to actually pick this type of algorithm. Okay, you can just see that, you can just look at this value. Okay, so this value, by looking at this value, you can see that if you have an solution that runs with 2 to the power n runtime, you can actually tell that this algorithm is never going to stop. Okay, and you are never going to find a result if you run a problem with this algorithm. All right. All right. So these are the all growth rate functions. And here we're saying how do we read them and how they make significant difference when our input size is growing. Okay. So 2 to the power n is a time requirement for an exponential algorithm. Okay. And it increases too rapidly. Okay. And it's not actually really practical to find a solution that runs into 2 to the power n solution. All right.